Hi, today Will and I would be discussing thermal conductivity, which is the movement of fluids due to a difference in temperature. Our lesson is derived from chapter 8.5 of Thermodynamics for Physicists by T.E.Faber. One of the first things to note is the difference between conduction and convection, which are two different ways by which energy can be transferred from one end of a fluid to another due to the difference in temperature. And we will start off by looking at conduction, and if I can just wipe this off. The thing is, conduction is when energy moves through a fluid due to the fact that some molecules of the fluid are of a higher energy, they're hot, and there are some molecules of the fluids of a lower energy, the cold part of the molecules. And so energy moves down the gradient by the higher energy molecules passing on their energies to the cold molecules. Next, we will look at convection, which is really, for this presentation, the more interesting of these two phenomena. So with convection, you have a body of fluid as usual, and you've got a cold part of the fluid shown by the blue lines and the hot part of the fluid. And convection occurs when the hot part of the fluid actually moves through the rest of the fluid, creating a current. This current drives heat away from the warmer body, and thus the warmer body becomes colder, and this heat is dispersed amongst the rest of the fluid. Giving a fluid at two different temperatures, so you've got the cold part and the hot part. If the cold part is of T1 and the warm part is of T2, we will use theta naught as the variable that defines the difference between these two temperatures.
The simplest problem we have here is that of a long cylinder immersed in a fluid. We model the cylinder as infinitely long, so we do not have to worry about variables dependent on the length of the cylinder. Instead, we take a planar cross-section and just use the radial variable. Theta naught can be considered a thermal counterpart to the Reynolds number. For instance, small theta naught can be considered the counterpoint to laminar flow. Here, the radius of thermal influence extends far into the surrounding fluid. For large theta naught, there's a relatively large counterpoint to turbulence. For instance, the radius of influence of the thermal diffusion would be small compared to the distance between two such cylinders, so there are no interactions between cylinders. And finally, for very large theta naught, we have the analog of a turbulent boundary layer. Here, in the small theta naught regime, the total heat loss Q can be expanded as a function of theta naught and theta naught squared. The higher order terms are discarded. C prime and C double prime depend on the size and shape of the cylinder and the nature of the surrounding fluid. However, for large theta naught, Q is normally proportional to theta naught raised to the 5/4. And finally, for very large theta naught, Q is proportional to theta raised to the 4/3. And here we come to the Boussinesq equations. These have been adapted from our normal fluid equations to include the thermal presence. This first equation is the counterpart to the Navier-Stokes equation. The second is for a fluid of approximately uniform density. This third equation assumes constant thermal conductivity and describes the heat transfer per time into an element of fluid per volume. We can derive the first equation by modifying the Navier-Stokes equation, specifically the part that deals with pressure gradients. These pressure gradients are based on density, and as we know, density changes with temperature. Therefore, when we have a temperature gradient, we have a density gradient and then a pressure gradient, and the fluid flows in the direction of the pressure gradient. Here, the fluid is at a uniform temperature T, with a small theta dependent on x, some distance variable, that is non-uniform across the fluid. This non-uniformity causes density gradients to appear in the fluid, which we will next model. We will replace our constant rho, which stands for density, with a function that, for density, changes with temperature. Here, alpha deals with the rate of change of volume with respect to temperature. We call this the thermal expansion coefficient. We can now replace the previous pressure gradient, as introduced by the Navier-Stokes equation, with our new one that includes thermodynamics. Here we have a regular Navier-Stokes equation. We will assume that convective flow is normally steady flow, where du dt is 0. Substitution in simple algebra gives us our corrected Navier-Stokes equation that includes thermal, and is the first of the Bossanesque equations.
For the second equation, we have that del du is approximately 0. And this is because for a fluid with a uniform density, del du is actually 0. But in this case, as previously covered, temperature and density are not exactly uniform, hence the need to approximate the 0, because the changes still really make a difference. For the third equation, we have that kappa times del squared of theta is approximately equal to rho times Cp times d theta dt, where kappa is the thermal conductivity, rho, as usual, is your density, and Cp is the specific heat capacity of your fluid. We can move some of these constants around in order to create a new equation where you have that kappa over rho times the specific heat capacity times del squared theta is equal to d theta dt again. And we can rewrite kappa p and Cp as xi, and we can approximate the other side to d theta dt, as we have previously covered in this class. However, even with all this, the problem still persists that these equations are actually rather difficult to solve on their own. And instead, in order to avert this problem, we use dimensional analysis in order to come up with new different dimensionless variables that can tell us more about a fluid. And so you have Q over K, which is in terms of temperature, theta naught, also temperature, A, which is in terms of a unit of length, and alpha times G, which is length divided by time squared multiplied by temperature. And you have V, which is a unit of length squared per temperature, and finally chi, which is a unit of length squared times divided by temperature as well. And so from these identified variables, we can come up with our new dimensionless variables, 3 new ones of course, and the first one is the Nusselt number, which is given by Q over kappa times theta naught, and this is temperature over temperature, hence why the variable is dimensionless. And next you have the Rayleigh number, which is given by Ra is equal to alpha g times theta naught times a cubed divided by chi times v. And there's a bunch of different dimensions here, but you notice they were all cancelled out. We have L per temperature per time squared per times temperature times L cubed, and eventually all of these can cancel out you can see the L's cancel out because you got 4 on top, 4 at the bottom. So does the temperature, so does the time. And for the final number, you have the number is the Prandtl number, which is actually a bunch of different constants and is given by PR is equal to V over chi, and the different constants involved here are the viscosity of the fluid multiplied the let me rewrite that. Once again, the viscosity of the fluid multiplied by the specific heat capacity or divided by kappa. And this is, of course, length per unit time divided by length squared per unit time, length squared. And once again, this is dimensionless. Following this, there are 3 pretty important things I think you should note about these different dimensionless numbers. First off, because of the Birmingham theorem, these are the only possible independent dimensionless combinations we can have given our number of constants or raw variables. All other dimensionless numbers can be written as a combination of these 3. The second thing to note is that absolute number is actually a function of the Rayleigh number and the Prandtl number, which we will discuss later. And finally, the Prandtl number actually exists as a constant that differs from fluid to fluid since it's made of constants.
Since the Prandtl number is made up of constants, we can uniquely determine what the Prandtl number is for many different situations. For air, it is 0.073, water about 6, and for liquid mercury it's about 0.025. Now, we know the Prandtl number, and we know the Rayleigh number, but we also know that the Nusselt number is a function of the two. Therefore, since we can have a constant Prandtl number, we can get a function that maps from the Rayleigh number to the Nusselt number. We can test this relationship empirically, and thereby test indirectly how reasonable our dimensionless numbers actually are compared to the Bose-Nash equations. To perform this test, we can measure the heat loss from various types of cylinders. We can perform these tests using variables of radius, temperature, and pressure. Therefore, we can make multiple tests keeping 2 out of 3 variables of temperature, pressure, or radius constant while varying the other. However, the book Fluid Dynamics For Physicists by T.E.Faber already has data collected by A.H. Davis. Here we see a log-log plot of the Nusselt number versus the Rayleigh number. As we can see, as the Nusselt number and Rayleigh number get larger, they form a linear relationship. However, keep in mind that this is on a log-log scale. Therefore, we may be reasonably confident in our evaluation of the Nusselt number as a function of the Rayleigh number and the Prandtl number. Therefore, our dimensionless numbers and Bose-Nash equations are most likely correct as well.